Hey everyone, welcome back. I want to talk to you today about how to add, subtract, multiply, divide, and keep correct numbers of sig figs. All right, if you remember the basic rules on how to determine the number of sig figs in the first place, this is going to be really straightforward. The rules themselves are going to be very straightforward. I want to start out with the addition. Yeah, right. Let's start out with the multiplication division rule, okay? I think it's a little bit easier to get a hold of. Okay, so here's our rule. This is for multiplication and division. The number of significant figures you can have in the result, that's your answer, in case you're wondering, the number of sig figs in the result is going to be exactly equal to the number of sig figs in the least precise measurement used in your calculation. Okay, so let's just come up with an example. Okay, so here's our problem. 3.45 times 0.21. First step, determine the number of significant figures you have. This one, 3.45, they're all integers. Looks like 3. The 0.21, how are you still confused about the 0 out front? It's a leading 0. Is there an integer out in front of it? Nope, so that means it's not significant. This one has 2. Now what this rule says is the least precise measurement used in the calculation. Who's the least precise? This guy, okay? So that means our answer can only have 2 sig figs. Now here's what you do. You don't do any rounding or anything, any kind of craziness first. You simply plug this number into your calculator to get an answer. So do that right now, get an answer for that problem. Now my calculator gets me an answer. Hold on a second. I just had some soup, so I had to cough a little. My calculator gives me 0.724 and 5. Now the thing is, I can only have 2 sig figs. Where do we start? Is this number out in front? Is it 0 sig fig? Nope, it's a leading 0. I like to underline my 2 sig figs, here they are. And now I like to put a little line up here and evaluate this digit. Okay, so is this a 5 or bigger? No. Okay, good. That means my answer, written to 2 sig figs, is 0.72. And that, my friends, is it. All right, let's try one more example. Imagine you are, let's just pick this number. How about 7.11? And I want you to divide it by 1.13. Okay, sig fig rule. I can only have the number as the least precise. Let's see. Blah, blah, blah. This one looks like it has 3 sig figs. You buy that? This one has 3. This one? Yep, it's got 3. Okay, what does that mean? Well, it means my answer can only have 3. So if I do this with my calculator, wait for a second, I gotta calculate it, and you should be calculating it too. This is perfect. I'm gonna give you exactly what my calculator gives me. 6.29203553. Wait for it. 3539823. And in the past, I guarantee you, at least one of you would have written that entire answer down as the answer on your page. Well, now you know, based on the rules of significant figures, you can say, hey, I can only have 3 sig figs in my answer. So where are they? There's 1, there's 2, there's 3. I put a little line up here. You don't have to do that, but I do. And I ask myself, is that a 5 or bigger? Nope. So my answer has to be 6.29. So now my answer has exactly the same amount of uncertainty as my 2 starting numbers have. This is why we use sig figs. Okay, let's go to another example. Okay, here's your problem now. I've done something a little tricky. I've put the numbers in scientific notation. This is 2.5 times 10 to the minus 3 and 7.11 times 10 to the 5. And we want to multiply those together. Well, same thing. You got to look at the rules of significant figures, and I'm looking at this, and this number looks like it has, do you remember? Does it have 2 or does it have 3 sig figs? If you remember, the sig figs only come from the numbers out front. So this one has 2, this one has 3. So my answer can only have 2 sig figs. So now the question is, can you plug this into your calculator? We'll have a little discussion in class on how to do that. So I'm going to do that right now. Okay, my calculator gives me 1,777.5. Now, we have a little problem. I need this in 2 sig figs. Here they are. And okay, fine. Let me just change colors. There's my 2 sig figs, and I put the little line up here. Is this a 5 or bigger? Yeah, sure. So what do people do for the answer? What's the answer right now? Well, people are going to say, oh, the answer is 18. And I'm like, really? Because if I gave you $1,777 and you had that in your pocket, and then in your other hand I had $18, is that the same thing? No way. So your answer still has to reflect something like what your starting value was. So this is a little bit tricky. Now I've actually has to put this answer in scientific notation. It's the only way to do it. So pause for a minute, go back to this number. How do I put it in scientific notation? Put the whole number right here. All right. So I know I need to get this decimal. Let me write the number over again. 1777.5. And if you remember, I've got to take that little decimal and I've got to make the little loop-de-loops. I got to move it to the left. I got to go 1, 2, 3 places. What does the 3 mean? Well, that's where I'm going to get my exponent from. I'm going to have 1.7775 times 10 to the 3. Now we can come back and do a little bit of our rounding. We remember before we could only have 2 sig figs, and that's the digit I want to look at, the 7. The 7 is going to make this become an 8. So my answer in 2 sig figs is going to be 1.8 times 10 to the 3. Okay, so this is a little bit tricky. We're gonna need to work on these a little bit. A lot of people don't like to do this step, right? So let's go on to the next sig fig rule. Okay, so now we're looking at the addition, subtraction, sig fig rule, right? The number of sig figs in the result depends on the number of decimal places in the least accurate measurement. You're going to notice this is a little bit different. So let me give you an example. Let's say I had a number 125.1 and I want to add that to the number 0.345. All right, so I'm adding these two numbers together. This sig fig rule now only looks at decimal places, and my answer can only have as many decimal places as there are in the least accurate measurement. So who's the least accurate measurement here? Yeah, it's this guy. This guy has 1 decimal place. This guy has 3. My answer can only have 1 decimal place. So if you add these two numbers together, you're going to get 125.445. And according to this rule, this is the only decimal place I'm allowed to have. Now, I don't change anything in this number. I'm only looking at the decimal point. Again, is this a 5 or bigger? No. So my answer with the correct number of sig figs is 125.4. Now, if you notice something, this answer has 4 sig figs. If you look at the starting values, this one has 4, this one has 3. So it's possible you might get confused based on the multiplication division sig fig rule. Remember, addition subtraction is a little bit different. Let's do another example. Okay, here we go. Next problem. 1.0115 minus 0.015. All right, when you do this problem, you get 0.9965. Okay, 0.9965. But because this is the addition subtraction rule, you can only have as many decimal places as are in the least value. So this one has 3 decimal places, this one has 4. Your answer can only have 3. So watch this. Here's 1 decimal place, 2 decimal places, 3 decimal places, and now I have to evaluate this number. This is a 5 or bigger. So what is that going to do? It's going to affect this number and this number only. So my answer, 0.997. Okay, so these are the addition, subtraction, sig fig rules. Okay, they're not that bad. Okay, so before we basically completed our talk about addition, subtraction, sig fig rules, but I want to throw something out there that's a little bit, well, character building, as I like to say. What happens if you encounter an addition, subtraction problem where the numbers are in scientific notation? What do you do? Well, you might be tempted to say, well, these numbers both have 1 decimal place, so your answer can only have 1 decimal place, but you might have to do something a little bit differently. You actually have to take these numbers and make sure that you have to actually change them so they have the same value of exponent. And it doesn't matter which one of these you choose. I just want to give you an example. I need the exponents to be the same before I can actually make a justification as to whether I want to, how I want to add them. So if you remember, if I want to take and increase an exponent here, I have to decrease the value of the number. All right, so let me just change that and move this over here. So I'm going to write this number over again. 2.5 times 10 to the 2. So the deal is, if I want the exponent to increase, the value of the number has to decrease. And I'm not talking about subtracting, I'm simply talking about moving a decimal. When I do this, I have to take the decimal and move it one place over here if I'm increasing the value of the exponent by 1 to 3. So this number becomes 0.25 times 10 to the 3. Okay? This number is exactly the same as 2.5 times 10 to the 2. If you plug them both in your calculator, you're both going to get an answer of 250. They're the same number. You may have done this before in math class. You could try it the other way around. Sorry. Take the number 3.7 times 10 to the 3, and let's say you want to bring the exponent down. Well, the rule is basically the opposite of what we had before. If you want to bring the exponent down by 1, you need to make the number up here go up by 1. And that means moving the decimal point one place over this way. So 3.7 times 10 to the 3 becomes 37 times 10 to the 2. Okay? So you have a choice on how you want to write that number. Okay, so if I actually want to go back and do this problem, it doesn't matter which of these you do. You get the same answer each way. So let's do, just for the heck of it, let's pick this method. Okay, I'm going to choose 0.25 times 10 to the 3. So let's write this over again. So now I can evaluate. I have 0.25 times 10 to the 3 and 3.7 times 10 to the 3. The sig fig rule says I can only have as many decimal places as the least value, which means this one, which means my answer can only have one decimal place. Okay, so go ahead and add these together. And if you do that, you get 3.950 times 10 to the 3. Now that is not rounded correctly. It doesn't have the correct number of sig figs. Remember, you can only have one decimal place. Where's your decimal place? Here. You have to evaluate. Is this number a 5 or bigger? Yes, it is. So what's it going to do to this decimal place? Guess what? It turns it into a 10, which turns this into a 4. So you are looking at 4.0 times 10 to the 3. Okay? 4.0 times 10 to the 3. Now, I want to do the problem the other way with the other answer, just to show you that they're both the same. Okay, so I've placed both of these numbers into the times 10 to the 2. Now when I come to look at this to evaluate decimal places, this answer has one decimal place. This answer has none. So this means my answer can have no decimal places. Okay, do the math. You get 39.50 times 10 to the 2. Okay, your calculator may have given you something a little bit different. I just kind of kept it in the spirit of the same scientific notation we have. 39.5, I can't have any decimal places. So this 5 rounds this up to a 40, and we get 40 times 10 to the 2, which if you change the answer around, move this number back down, is exactly the same, 4.0 times 10 to the 3 as we had before. Okay, so this entire rule is a little bit more advanced. You will definitely have to practice this a little bit, and I think that's good for today. Right now, we're moving on after this. We're going to be talking about combined problems. What happens if you had an add and addition and a multiplication problem in the same problem? That's the subject of our next lecture. Have a great day. We'll see you tomorrow.